Hi everyone, welcome to my short presentation for the course project for Machine Learning Foundations for Product Managers. I would like to directly jump since I have a limited time here, only 5 minutes. So we are given a project to predict the combined cycle power plant's electrical output, which is this one here, the target value, by using the features that's given as temperature, T, AP, RH, and V. And we have also given the dataset directly, and we were asked to complete a complete training of an AI model, minimum using 2 different ways to compare them and also evaluate the results. I would like to directly jump to my project. So in that case, I'm looking at the description of the project and also the data, so I can say that the target value is a continuous value that we were trying to predict. So it's gonna be, in that case, probably a linear regression model and not a classification algorithm. And the next thing is we do have the historical target value, so it's gonna be a supervised learning. And with this machine learning approach decisions, I'm also thinking that I might evaluate different algorithms for regression that we will see with the data. And my output matrix is going to be either mean squared error, MSE, or mean absolute error, MAE. However, I might use both of them because I do not have the expertise to say that if outliers matters or not in that case. And that's why I might use both of the metrics to evaluate the different models. So first I start with installing and importing the different libraries. So I need mathematical libraries, data libraries, and also sklearn for the machine learning. After importing these libraries, I would like to import my data set. So first I upload in Jupyter Notebook my CSV file that I received, and after that I'm using this PD read command to actually upload the data set. And this is just a visualization of the first 5 rows to see that the data is there. The next thing that I'm doing is statistical analysis on the data to see that we have a complete data, nothing is missing, so you will see from the values here. And also that there is not obviously wrong values inside the data, so you will see that also by looking at this deviation. And after that, the next thing that I need to do is plotting a kind of output diagram. So this gives me a feeling about where is my output more or less lying. So for example, this is my normal output. Later on, if I'm kind of using my model and if I would predict something like 1000 here, that I would see that it's completely out of the value that it should be. So the next thing is checking the target value against different parameters, different features to see their relation. And this is going to help us to decide also the algorithm to be used. So the first one is I'm checking is here the electrical output against the AT. And the relationship after a scatter plot is obviously a negative linear relationship. And this negative linear relationship strongly suggesting that we can use a linear regression with degree 1. And this would actually represent this relationship. Here you see the cursor. And after I'm plotting the other features such as PE, V, and in that case, it's still a kind of linear looking relation. However, this gives me the feeling it might be a parabolic relation, as you can see here. It might be a negative parabolically related. And in that case, it suggests that it would be also an option to use a polynomial regression model. So to a degree of a linear regression model to improve our model. Also, the third and the fourth feature is suggesting similar things as the second one. So they are a bit more noisy. However, there might be a parabolic relationship, for example, here between the RH and also between the AP. But also the relationships could be linear and just like a lot of noise is inside there. And especially the RH is including a lot of noise. So this could be a feature actually that can be excluded to decrease the complexity if you would have a lot of features. But we do not, so I decided to use all the features in that case. And now I'm going to start to actually do the training my models and comparing them. So summary is I'm going to use linear regression and polynomial regression, 2 algorithms to compare, to train and compare. As a feature set, I'm going to use all the features that I have because I have a small feature set, so I do not want to exclude. However, it could be thought that maybe RH can be excluded and tested. And as output metric, I'm going to use both MSE and MAE to test the performance of the different algorithms. If I would have a more expertise in the area, maybe I could have decided if outliers matters or not. Depending on that, I could use MSE or MAE. The next step that I'm doing is I need to split my data into the, first of all, train and test data. Training data is 80% and the test data is 20%. That's just like generally used like that. It could be different, of course. And then I decide to use a cross validation for the validation set, and instead of a fixed value set, that I would like to have a k-fold validation that actually helps me preventing the kind of random high predictions, or also helping me not to overfit to the data. So, or if there is an overfitting, to really spot that. So the next thing is I need to split my columns into X and Y. In this case, X is the features that I'm going to use, and the Y is my target value, which is the electrical output. Then split the data into the train, validation, and test sets. You see it here. And after splitting them, then I'm going to start to train the first model. And the first model is the linear regression. And linear regression, I'm creating a model instance. After, I'm creating a k-fold instance with the splits of 5. And then I'm shuffling the data also. And then after this, I train the data, and then I also calculate the mean absolute error and also the mean squared error. And in that case, I see that the first algorithm after training in the validation test, validation k-fold validation, it shows me a MSE for -20. The minus sign is coming from here, from this negative mean squared error, because it's a convention that actually helps us to order the things. However, we could also think as an absolute value. And the mean absolute error is actually 3.7. So these are my results from the first linear regression. Now I'm going to do the same training with the same data, but this time I'm going to use a polynomial regression. And in polynomial regression, I have a chance to arrange the hyperparameters. Hyperparameters are the degrees that I'm using for the features, right? The square or the cube. And I decided to use 3 of them just to test and then see that how is the performance of the algorithm. So I have a for loop here to actually train the algorithm 3 times for different degrees here, and then using them each and every time with a cross validation, and then cross validation will show the scores to me about MAE, MNC, and then I will print each of them for each for loop. So actually here we are kind of training the algorithm 3 times and running it over the validation set. So you will see that actually MSE on the validation set, also MAE, is better than the ones that we have seen for the linear regression. We will compare later. But also, if you look at the degrees, when I increase the hyperparameter, actually the performance of the algorithm is getting better. So here -16, 3.26. And in that case, the choice would be, for example, a degree 4. We could actually increase more and check if it gets better. Or in a real life case, we could say that the difference is too small to be important, so we could actually use a degree 2 polynomial or a linear regression to say that we do not want to increase the complexity or interpretability of the algorithm. So, but for the sake of this project, I'm choosing the degree 4 polynomial regression because this gives me the best results until now. And then after this, what is very important is that to test my final algorithm, that's my decision, is on the test data that we separated at the very beginning, and we did not touch it at all to prevent leakage or any kind of like a bias. So that's why now I'm here testing my trained model on the test data. And I also calculated over the test data for the linear regression to see also how my linear regression is acting on that. So I will see that actually polynomial regression acts much better with 16 MSE and 3.15 on the test data. And then in that case, my choice of polynomial regression was actually justified here. And these are my data. However, you see that still we have a high mean square error, meaning that we have some outliers in the predictions that we can see here. But when we think about the distribution, 450 more or less, and it's only 3.15 variance here, the mean absolute error. So actually we have quite a good algorithm to predict the output of the electricity. So I just want to see my algorithm in action. So I'm preparing one row with the features, and when I give these features to my trained algorithm, which is actually a real life case because this data was not inside any of the sets at all, so I will see directly that the prediction is 453, and also depending on our distribution curve, actually it's a pretty realistic, in that case, prediction. So voila, so our model is working and predicting what we want to have. And the last thing that I want to see is the performance that we already analyzed in a graphical way. So I'm plotting a scatter plot by, this is actual versus predicted values for the test data. So you will see that this black dashed line. So if our algorithm would be perfect, actual values would be always equal to predicted values, right? So it will be always on this dashed line. And we see how our algorithm performed with the blue lines. And the reason for MSE was higher is that you see a couple of here outliers. This made our MSE actually higher. But if you look at the general prediction, we are always on the line, and we are actually pretty good performing on the predictions that we have on the test data. So all in all, we can say that the choice of the algorithm and also output metrics was successful, and the model can be used for predicting the electrical output. So that's the end of my presentation. Thank you very much for watching or reviewing, and looking forward to connect. Thank you.